All right, we're talking about rings. We're going to talk about ring homomorphisms. We have homomorphisms for groups, and a ring is really just kind of a special group, right? Because the addition, the ring under addition forms an abelian group. So we're going to extend this idea to a ring homomorphism. So we also have this multiplication of the ring. We're going to preserve that as well. So here's the definition. We're going to require, this is basically the group homomorphism part, right? The group element plus the group element has to equal phi of A plus phi of B, where this plus occurs in S and that plus occurs in R. But we're going to have one more requirement too. Because rings have multiplication, we're going to require that when you multiply together two elements and then map it, that's the same as mapping them separately and then multiplying. Where again, this multiplication occurs in S and this multiplication occurs in R. That's the definition of a ring isomorphism. So it's just basically like a group, it's a group homomorphism, but then we're going to throw in that you have to have the same homomorphism property for multiplication as well. And of course, if it's 1-to-1 and onto, then we have a ring isomorphism. So that idea should be exactly the same as with groups. So the image is just going to be the exact same definition of as a group homomorphism. There's literally no difference. It's just that something maps to it. So it's all the S that something maps to it. The kernel is again going to be the exact same definition of for a group. It's the things that map to the group identity, the additive identity. So here's an example. If we can map the integers to z mod 6, and we're going to do it by just mapping it to just reduce things mod 6. Then we're going to show that for all a and b, we can see what happens when we add phi of a and phi of b together. Let's take a look. Well, we get a mod 6 plus b mod 6, the same as a plus b mod 6, and now that's just phi of a plus. And so we're halfway done showing that it's a ring isomorphism. We've shown it's a group isomorphism, but now we need to show it's a ring isomorphism. So we multiply phi of a times phi of b. It's defined to be a mod 6 times b mod 6, where I just reduced a and b mod 6 separately, but that's equal to ab mod 6, which is equal to phi of ab. Therefore, we've shown that phi is a ring homomorphism. And now we can just check out some other things like in the kernel. And the image is pretty clear that you can get everything. Why is that? Well, phi of 0 equals 0, phi of 1 equals 1, phi of 2 equals 2, phi of 3 equals 3, phi of 4 equals 4, and phi of 5 equals 5. And these are all the elements of Z6. So we have an onto map. The kernel, well, the kernel means that we have to find all the a such that phi of a is equal to 0. But if we're reducing mod 6, that means it's going to be all multiples of 6. And that's just 6z. So that's the image in the kernel. And phi of 0 is equal to phi of 6. Both of them are equal to 0, so we're not a 1-to-1 map. So we don't have an isomorphism. But it is onto, as we said here. All right, here's another map. I'm going to map from the integers again. The integers are the standard example of a ring to the 2x2 matrices that have integer entries. And I'm going to map phi of a to be 0, 0, and then whatever a and a is. So phi of 2 would equal 0, 0, 2, 2. Then let's see, for all a and b, phi of a plus phi of b is defined to be two matrices. Just exactly that. Now, I'm just going to work in the matrices. I'm just going to add these two up and see what happens. And I get this matrix. Oh, but this is exactly phi of a plus b. So I get a group homomorphism, and I'll just check to make sure it's a ring homomorphism. So if I multiply them together, that gives me a multiplication of two matrices, like that. Now I just multiply them together. It goes 0 times 0, 0 times 0, 0 times 0, 0 times b. Sorry, 0 times 0, 0 times b, 0 times 0, 0 times b, a times 0, a times b, a times 0, a times b. And you get exactly that. and that's equal to phi of A B. And so we have homomorphism, and now we can check out the image and the kernel. Well, once again, if you pick any, right, everything has this form. Or sorry, right, so these are the only things we can get. So we're not going to get an onto map because all the 2x2 matrices, this is all the 2x2 matrices. So there's no way of getting 1, 2, 3, 4. Because the only thing that I can get out has to have zeros at the top. And there's no even way to get out 0, 0, 1, 2. So this image, this is far from onto. Let's see what the kernel is. The kernel is just the things that map to 0. And how do you make this a zero matrix? Well, A has to be 0. So we have a one-to-one mapping, but it's not onto. Because, right, showing that the kernel is just equal to the identity of the input ring. So we have one-to-one not onto map, so, well, it's not an isomorphism. Here's another example. We're going to map Zi. Zi are all the elements of these forms. It's almost like the complex numbers, except you can't have any real numbers. You just have to have integers. So you could have like 3 plus 4i, negative 7 plus 16i. Like, they're elements of that form. So I'm just going to change the plus to a minus. So, so basically, I mean, that's just it. I'm just going to negate the sign on the imaginary part. Let's see. Then, for all A, B, C, D, let's see what happens. Is this going to be a homomorphism? Well, let's see what happens. Add these two up. Well, by definition, that's going to be A minus. That plus turns to a minus. That plus turns to a minus. And we get just that. Let's do some rearrangement in the codomain. And we get this. Oh, what's this defined to be? I could change the minus back to a plus, and I see that that's equal to phi of that thing plus that thing, right? Phi turns this plus to a minus, and so we're good. So we have a group homomorphism. Now let's just make sure that multiplication holds and see if I have a ring homomorphism. Multiply, and then I'm going to map. I get that. Now let's multiply it out. So I have to use the distributive law, or FOIL, and what do I get? I get this thing. What's that equal to? Well, this is precisely equal to what happens if I turn that negative into a plus. So, right, it's definitely true that phi of this thing is equal to that thing, because the only difference is that that plus turns into that minus. But what's this equal to? Well, if you multiply these two out in the domain, you end up with this. So we really do have a ring homomorphism here, and let's just see what the image and the kernel are. It's onto because, right, pick anything in here. Anything in there has the form C plus di. Well, what maps to it? Well, C minus di is going to map to it because I just changed the sign in the middle from minus to minus minus, which is plus. So it's onto. Is it 1 to 1? What's the kernel? So if the kernel is trivial, then I get it's 1 to 1. So let's suppose I have that phi of something equals 0. This is how I check to see what's in the kernel. That means that A minus bi has to equal 0, which is the same as writing 0 plus 0i. So that means A equals 0 and B equals 0, and this thing had to be 0 to begin with. So we're going to get 1 to 1. So now we have 1 to 1 and onto. So it's an isomorphism. In this case, an automorphism because it maps it to itself. But yeah, it's an isomorphism. Great. So here, these are all polynomials with integer coefficients. So this is like 7x to the 9th minus 6x plus 3. Like these are the inputs, and the output is going to be just the integers, where I just plug in 0. So if this is equal to f of x, the way I map it over is I just see f of 0, plug in 0, and that's going to give me 3, because it's just a constant term, basically. This is going to be a homomorphism. Check it out. So for every two polynomials, right, this is code for polynomials. What happens when I do this? I get f of 0 plus g of 0. And that's equal to a function that I could call f plus g of 0. Now that's this. Oh, and I should point out that this is equal to phi of f of x plus g of x. So we really do have a group homomorphism. Now let's just see if it's a ring homomorphism by checking the multiplication. It's equal to f of 0 times g of 0. And that's going to be equal to f times g of 0. And that's going to be equal to phi of f times g of x. And that I can separate out, and I should really do one more step here. That's equal to phi of f of x times g of x by definition of fg. So I get that these two things are equal, so I really do have a ring homomorphism. All right, let's see the image in the kernel. So phi of the constants would be easier, but right, if you let a belong to z, we're going to get an onto map. Why is that? Just to make clear that it's a polynomial, you could use the constants because constants are polynomials. Phi of x plus a is equal to a, so it's onto. Also, let's see what the kernel is. The kernel is all the things that have a0 equal to 0, because when I plug in 0, right, if I have 0 equal to phi of f of x, that means this is defined to be f of 0, so we need f of 0 to equal 0. Well, that means that this equals 0, which means that that's the same as f of 0 equaling 0. So it's the things without a constant term, basically. So it's easy to prove that phi is onto, but it's not one-to-one. Phi is not one-to-one. All right. Oh yeah, here's an example. So ring homomorphisms are group homomorphisms, so we get all the goodies that we got from group homomorphisms to apply, at least apply to addition, not necessarily multiplication. And then when several of the same properties will apply to multiplication too. So let's take. So this we don't get from the fact that it's a group homomorphism. We do get this: n times r is equal to n times phi of r. That we get from a group homomorphism. But the proof is basically the same for this. This is a simple induction proof, and I encourage you to do it on your own. We also get if things commute, then these things will commute. So that's very similar to, right, this is with multiplication in the ring, so we don't know this from group homomorphisms, but the proof is exactly the same. Right, this is basically the proof. And there we go. So that's an introduction to ring homomorphisms. Thank you.